Okay, good afternoon, everyone. Welcome to today's um, joint ECECS Distinguished Seminar. Um, so before we start, I would like to actually give you a bit of sort of instructions. So we usually have our questions at the end. We take questions at the end. So feel free to leave your questions at any time during the talk in the chat. Also, our speaker today will probably pause at certain times to take questions as well, so we can do that as well. With that, I start introducing our distinguished speaker today. It's our great pleasure to have Professor Jiasi Chen from University of California at Riverside. She's an assistant professor in the Department of Computer Science and Engineering there. She received her PhD from Princeton and her bachelor's from Columbia. She also has some experience in industries, in AT&T Labs and NEC Labs America. Her research interests include edge computing, wireless mobile networks, and multimedia networking, with the recent focus on machine learning and AR, VR applications on mobile devices, which is a topic of her talks today as well. She's also the recipient of an NSR Carrier Award in 2020 and the Hellman Fellowship. So with that, I would like to welcome again Professor Chen, and the floor is all yours.
Great. Hello, everyone. Thank you very much for the introduction, and good morning, or I guess good afternoon for you guys. So yeah, my talk today is called Network, Augmented, and Virtual Reality for Mobile Devices, and I'm really pleased to be giving this talk here, especially during in this virtual format when we don't get to give talks as much as we used to. So here's an outline of the talk. I'll first be talking about what is AR and VR. You probably heard these buzzwords a lot in the news or in research, but I want to demystify that a little bit for you in terms of the system challenges. And we'll be talking about particular challenges and problems we find in terms of latency, accuracy, and energy metrics. Next, I'll be talking about my group's work and talking about two pieces of work. One is improving single user AR with deep learning offloading. And the second is improving multi-user AR through efficient communications. And finally, I'll conclude with some future directions that I'm really excited about in the space of AR, VR, and also mobile machine learning. So that's where the outline, and let's get started. So what is AR, VR? Let's try to give some context in the context of multimedia networking. So we start off with content creation, going to compression, store this content, and then eventually distribute this content over the internet or the network. And for the end users, what did we originally distribute? We were originally distributing audio like phone calls. Then it started getting a little more challenging. We started distributing on-demand video with high throughput requirements. Things got tougher and tougher, where we're delivering like live video streams with really stringent latency requirements. And now we're maybe at the stage where we're trying to deliver virtual and augmented reality data over the network to multiple users. So what is AR, VR? And you've probably heard these words, like people usually say AR, VR all together, right? But they're actually a little bit different. So let me try to disambiguate these two terms for you. So we can consider this on a spectrum where we have, on one end of the spectrum, we have reality, like if we were in a classroom with a seminar today. On the other end of the spectrum, we have virtual reality, which is where everything is all virtual. So all the characters are virtual, all the backgrounds and so on are also virtual. And in the middle of the spectrum, we have things like augmented reality or augmented virtuality. So in augmented reality, most of the world here is real. So the sofa, the fireplace, and the carpet are all real. And there's a few virtual elements overlaid on top, like these Lego blocks here. And in augmented virtuality is more towards the virtual end of the spectrum. So most of the world here is virtual, like all the grass and the pond here is virtual. But the real elements we have are the person's hand and touching this real keyboard. So one end you have virtual reality, the other hand you have reality. In the middle you have augmented reality. So who's using virtual reality? You have both smartphone-based hardware, things like the Google Cardboard or the Google Daydream, where you sort of slot your smartphone into the front of these devices, and the smartphone screen acts as the display for the VR. And you may also have external controllers like this Bluetooth enabled controller here that talks to your phone and lets you interact with things in the virtual scene. You also have higher end hardware like the HTC Vive, the PlayStation VR, or also the Oculus Rift. And that seems to be sort of where the trend is going. The smartphone-based VR is not as popular. I think Google actually shut down their Daydream division, but things like the HTC Vive or the Oculus Rift are becoming very popular, especially actually during the pandemic. We had a lot of trouble getting these devices for research purposes because they were all sold out because everyone wanted to escape their homes in the virtual world. And what about augmented reality? So just like virtual reality, we also have this division between sort of smartphone-based stuff and specialized hardware. So for smartphone type AR, the canonical example now is Pokemon Go. You could consider something like Google Translate as augmented reality because you overlay the real sign in a foreign language with the sign in English. Or something like even like Snapchat filters are considered augmented reality because you're overlaying these virtual elements onto your real world face. So smartphone-based AR is pretty popular, and you also have the emergence of more specialized hardware like the Magic Leap or the HoloLens, which are head-mounted displays and let you look through the lenses to see things overlaid onto the real world. And you also have a lot of interest from mobile phones, mobile platforms. So Google has Play services for AR, formerly called AR Core, which enables Android devices to support AR. And you have Apple ARKit, which enables your iPads and iPhones to support AR. So we see a lot of interest both from the hardware side and from the software side. So is it all just fun and games? Because most of the examples you probably see are like Pokemon Go or Beat Saber or some games, right? But AR VR has applications in many areas, such as data visualization, out of order, education, and public safety. But as researchers, we want to understand what are the engineering challenges of the platforms underlying these applications. And that's what we want to focus on, especially as computer network researchers. So in my mind, I classify AR as sort of processing input from the real world. And that's closely related to computer vision and robotics fields. And VR, I kind of classified them more as trying to output the virtual world onto your display. So it's more related to rendering and computer graphics. But don't get me wrong, all of these areas are closely related in AR and VR. So let me further disambiguate how AR and VR work. And I'm going to be using a common example of this Pokemon. So the top row is going to illustrate what happens in VR, and the bottom row is going to illustrate what happens in AR. So in VR, we have this virtual Pikachu character here, and we need to generate the virtual world and place the virtual Pikachu in this virtual world. So both the background scene and the Pikachu are virtual. And we also need to do device tracking to identify where the user is in the real world and map that into the virtual world and place the user in the virtual world. So here the user happens to be facing the Pikachu. And then we need to render. So we need to render what the user is looking at. So in this case, we need to render both the Pikachu and the background. And then finally, we display through the headset. Each eye sees a slightly different view of the Pikachu to account for the different point of view of each eyeball in your head. So that's it for VR. And let's take a look at AR, which has both commonalities and differences. So the AR example, we're no longer placing a virtual Pikachu in the virtual world. We want to place in the real world. So suppose I'm visiting UCR campus and I need to figure out where to place the Pikachu. First, I need to figure out where is the user in the real world. So once I localize where the user is, let's suppose the user here is looking at the sign. Then I need to figure out where to place the Pikachu in a logically realistic position. So in my example here, I want to place the Pikachu on top of the UCR sign. So I need to do some kind of object detection to figure out that, hey, this is the sign that is here, and it's a reasonable location to place the Pikachu. After I do that, then I get to place the Pikachu on top of the sign, so that when the user looks at it, it looks like the Pikachu is sitting in a reasonable location. Once I've done all these steps, then I can, just like in VR, I can do rendering. Here, I only need to render the Pikachu. I don't need to render the background. And I might need to adjust the lighting of the Pikachu, slightly darken it to fit in with the real world surroundings. And then finally, I display through my AR glasses, the Pikachu will appear on top of the sign. And please excuse my Photoshop skills here, but I assume that you can get the idea. So you can see that there are similarities and differences between AR and VR. VR has to generate the whole virtual world with the character and the backgrounds. AR only has to generate the virtual character. Both AR and VR have device tracking, which are really important steps. But in AR, the device tracking happens on a much larger scale because the AR user can move anywhere in the real world. Whereas typically in VR, the user is using it in like a bedroom or a living room, so a more constrained area. Great, so hopefully that helps you understand how AR and VR work. And what are some challenges that we find? And specifically, we're going to focus on mobile AR, just because for the talk, I wanted to focus on one of them and not overload you with information. So what are some problems that we see right now in mobile AR? So I repeated this picture here of the AR processing pipeline. And I made these two steps, device tracking and real object detection, larger in font. And that's because I want to emphasize their importance and difficulties with these two steps. So let's take a look. So to do object detection, to detect where to place the Pikachu, that can often be done using deep learning. But we run experiments and we check what the latency is of running, let's say, deep learning on a single frame. So it ends up being quite slow. This is 600 milliseconds per frame, which was reported in this DeepMon paper a few years ago. And that's quite slow because typically for AR, we'd like the interactions to be much faster, maybe in the order of 100 milliseconds would be more ideal. And we also observed really high energy drain from running kind of deep learning things on the phones. We measured it at 1% of battery per minute on a smartphone, which would be irritating to the user and also makes the smartphone overheat, which is uncomfortable. So that's for object detection. And for device tracking, in AR, this is typically done using SLAM, which stands for simultaneous localization and mapping, which tries to localize a user in the real world using a combination of inputs from the camera and the IMU sensors on the phone or mobile device. So we measured the latency of these of SLAM on mobile devices, smartphones. We found the latency is about 30 milliseconds per frame on a smartphone, so which is not too bad, but we will see more problems when we start talking about multi-user scenarios. And the energy drain can be quite high, 1.5 watts on a smartphone, and this 1.5 watts is after we subtract out the OS and the screen. So there's been work on trying to address these types of issues as well. So let me show you some examples. So here's an example of latency for a single user running on a smartphone. And what you're going to see is that in this video, the user is going to rotate around the scene. And we'd expect these annotations to pop up swiftly. But what you'll see is the annotations are kind of laggy, or nothing is popping up here, right? We should be able to detect this pile of papers. It's erroneously detected as a chair. Nothing is coming up here. We should be able to detect this potted plant, but it's kind of slow. It took a few seconds to pop up, and so on, right? So this is an example of latency for a single user. We also observe latency across multiple users. So let me first define what we mean by that. So suppose Alice places a virtual object here on top of the laptop, and then Bob sees the same virtual object from a slightly different angle. And we count the time from when Alice places the virtual object to when Bob sees the virtual object as a multi-user initialization latency. So when we measure this, this measurement's done over a public LTE network. The y-axis is the CDF, and the x-axis is the end-to-end latency. So please just look at the blue line here. You can ignore the red line. So we can see the end-to-end latency for multi-user scenarios is quite high. Median is about 15 seconds, which is pretty, 15 seconds is a long time, right? So you're kind of waiting, you ran your AR app, you're waiting for these two things to appear. You're like, what's happening on TikTok? So this is kind of detrimental to user experience. Other problems we also find are energy. So I gave you some energy numbers here earlier, but I want to put this in context of other common apps that you run on your phones. So if this is the power on the y-axis, and the x-axis is different types of applications. And again, this is the power after we subtract out the screen and the regular OS of the device. So if I'm just browsing the web, Google News, not too much, less than 1 watt. Even YouTube on your phone seems to be pretty well optimized, so not too bad. But once we start getting to things like ORB SLAM, remember I told you SLAM is a key component for AR, we start getting higher and higher. Tiny YOLO is a deep learning method, and we ran it on the phones, and we find it takes about 2 watts on average. So we can see that the AR components, the ORB SLAM and Tiny YOLO, can be pretty energy hungry compared to apps that you might typically run on your phone. So far I've talked about latency and energy, and the third metric I promised you is talking about accuracy. So what we mean here is the accuracy of the placement of the virtual objects. So in this video, what you're going to see is this 3D object here, this 3D axis here is the virtual object, and you're going to see it kind of moves around in space. This video is taken in one of my students, Shukan Ran's home, so sorry for it's a little bit messy, but you'll get the idea. So the user is moving around, and you see this virtual object randomly kind of drifted over to the side, then after a while drifted back. So this is what we call accuracy for a single user, because a single user experience, over time, the virtual object is drifting. We can also define a similar situation for multiple users. So here we have 2 users, Alice and Bob. And Alice is looking at the virtual object from one angle, and you see this virtual character here is sort of on the edge of the paper, right? But from Bob's point of view, the virtual character is in the middle of the paper, and it's also larger for some reason. So we call this type of inconsistencies, we call this spatial inconsistency. And it's a type of inaccuracy when multiple users view the same virtual objects. All right, so I've sort of bombarded you with all these metrics and problems that we find, and I just want to sort of link them all together. So we can think of different stages of the AR processing pipeline, especially in the multi-user scenario. First, Alice is doing some computation. Alice communicates information to Bob, and then Bob is running some computations. So over time, the latency will increase linearly, and the energy will also increase maybe by different amounts during these different stages. And the accuracy we determined is based on what Alice sees, what Bob sees, which is from the first time period to the last time period. And we want to compute this accuracy. So all these steps are related, and the individual stages of the processing pipeline impact the latency, accuracy, and energy. So they're all coupled together. And ideally, what we'd really like to see is some desirable points on this space. So if we look at the 3-way trade-off between accuracy, latency, and energy, we really like to have low latency and high accuracy, and also low energy. So this is where we want to live. Okay, and so that's what I want to say, my little intro about AR, VR. Hopefully you got the idea. And I guess one final point I wanted to make is that what I often see, or what I kind of get worried about sometimes, is that people are treating AR, VR as just a video stream, right? It's just another form of multimedia. We'll just treat it as like high throughput, low latency. What I want to say here is that I believe, in my opinion, we can't really treat AR, VR as a video stream and apply whatever existing multimedia networking techniques exist out there, because AR is not a video. The data that's being transmitted or communicated in AR is things like point clouds, 3D models, and texture files. So it's a completely different type of data. And in the case of VR, we can consider VR as like video in certain special cases, like 360-degree video streaming. But more generally, data in VR is 3D models and texture files. So it also has different characteristics than pure video streams. All right. So that's it for the sort of intro portion. And then I guess I would like to move on to some individual works that we've done in this space, now that I've introduced some of the problems to you. But here I'll just take a 2-second break, and then if people have any questions about the intro, I'd be happy to answer them of like sort of this overall space. Okay, great. If not, then we'll move on. So let me talk about some of our group's work. And the first piece of work is trying to improve single user AR with deep learning. So the premise or the goal is to reduce the latency for augmented reality. And the premise is that AR requires a lot of computation power. And we want to run these expensive computer vision and machine learning algorithms as part of the processing pipeline. So you have a couple of choices. Maybe you could run on the device. That ends up being quite slow, especially with the constraints of the hardware. Although there's been a lot of work in recent years for sure on making like machine learning algorithms run efficiently on resource-constrained hardware. Maybe you can run this processing on the cloud, but that would entail taking the data from the device, shipping it through the base stations, through the internet, all the way to the cloud, doing the processing there, and shipping it back. So you're gonna incur a long RTT to send the data that far. And so one solution that we might have is trying to run on the edge, and there we could take advantage of some nice compute nodes, some compute resources that are located on the edge node, and run things quickly on the edge. And I see a question in the chat. I think it's thank you for asking. So the question is, do you see a big difference in the problems for AR via handheld versus a data set? Yeah, that's a great question. So it's a little bit harder to work with the headsets just because they have like their own chips and they're not very programmable. So it's a little bit harder to like play with them and get like the same level of detail that we can get for smartphones, because like the measurement tools are way less mature. And also the AR headsets are developing like custom hardware, right? So to be honest, we haven't experimented a lot with the headsets. We've mostly been focused on the phones because it's kind of easier to play with, but I think it's definitely really interesting to look at it. I would say in our initial experiments with the headsets, we have observed similar problems like I showed you in all these examples on the phone that I was just showing you. So I think we see like similar problems basically. Cool. And then I'm not sure how to use this, but does someone raise their hand as well? Okay. Yeah.
I don't see anyone, so I guess.
Okay, great. Thank you. Cool. Yeah. So where were we? So let's continue. So what are challenges with current approaches? Current approaches for machine learning on mobile devices can be like local only processing, things like Apple Photos, Google Translate, or using GPU speedup. But like we said, when we ran experiments with reasonably high-end smartphones, we still found it's pretty slow, almost more than half a second per frame. You could do remote only processing. That's what like Siri does or Alexa does. They just ship everything off to the cloud for processing. That can work pretty well, but it can sometimes not work well when the network is bad. If you're walking away from your house and you're using Siri, Wi-Fi drops, it hasn't connected to LTE yet, you're gonna get a bad response, slow response. So our main observations are that different AR apps have different accuracy and latency requirements. The network latency is often higher than the GPU or CPU processing time on the edge server. So basically the network quality becomes really important when you're deciding where to do the processing. And we also find that the input video streams from the camera and the deep learning models have certain hyperparameters that you can tune to make them scale gracefully based on the amount of resources that you have. All right, so let's see what that actually means. So our problem statement is, how should the mobile device be configured to meet the latency and accuracy requirements of the AR app and therefore the user? So our solution at a high level is to periodically profile, optimize, and update this configuration. So what this looks like is we first do a bunch of offline performance characterization, then we do some online optimization for the configuration, then we update the configuration, and then we keep doing this online feedback loop based on the current performance. So that's a high-level view of what's going on. And let's take a look at what this decision framework actually tries to change or modify. So we basically have a bunch of degrees of freedom on the left. These degrees of freedom could include the input camera resolution, the neural net model size, whether to offload or not. These are choices that we can make. And the metrics that we want to optimize are things like latency, the accuracy, or the energy. And we don't have a really good understanding of the relationship between these degrees of freedom and the metrics, right? They're kind of just these general nebulous points in these two spaces. So we want to optimize the function from the degrees of freedom to the metrics under certain constraints. But how we do that is not that clear because we don't have a clear understanding of the relationship between these two, the degrees of freedom and the metrics. And we have more detailed things about what you can actually optimize. That's probably more detail than we need here, but I just want to give you an idea. So let's look at the system design. We have an edge server, we have our front-end device, which is say our smartphone, and we have some input camera stream. And what we want to do is input this camera stream and output this display. Maybe I want to detect the car so that I can place this dinosaur next to it. So I have a bunch of constraints as well. These constraints include the battery constraints, the network conditions, the requirements from the application, like the accuracy or the latency. And what I'm first going to do is profile how the front-end device reacts to these different constraints. So if I run, if I want to understand how the latency changes as a function of accuracy, or I want to understand how the battery changes as a function of accuracy, I'm going to profile the performance of the device by tuning a bunch of hyperparameters and see what points exist in this multidimensional space. Once I have an idea of the performance, then we can then do some kind of online decisions. And the decisions that we can make are either to choose to run a nice big deep learning model on the device. We could run a small deep learning model on the device, or we could ship that all off to an edge server and do some nice deep learning over there. So these red arrows here indicate the different choices that we have and eventually want to have an output display. So what are some metrics? For AR, we have both the classification and location are important. So we use something called the intersection over union metric, which is a common metric in object detection area. And that measures how accurately you've both placed the object with respect to the ground truth, and also whether you've correctly classified the object. And for our purposes, for our ground truth, we use a big deep learning model running on the highest resolution, assuming that is doing a good job. And we also care about a bunch of different timing metrics. So latency is sort of the time from when we sent the frame for processing to the machine learning model to when we get the result. And we also care about the continuous timing, so the frame rate, which is the time that it takes to process consecutive frames. So we've done a lot of performance characterizations. I don't want to show you all of them because it's just going to overload you with a bunch of graphs. But I did want to show you one of them, which is showing the trade-offs between latency and accuracy. Because I mentioned earlier in my introduction that we have the three-dimensional space, and we want to try to have a good combination of accuracy, latency, and energy. So how does accuracy change with latency? If we look at time t equals 0, let's suppose I'm looking at this moving car. And because of some delay with the processing, by the time I get the result, I may be highlighting the wrong part of the scene because the car has already moved on. So this gives us a trade-off. This gives us a relationship between the deep learning and latency and accuracy. So we plot this. On the x-axis is the processing latency, and on the y-axis is the accuracy. So we can see as the latency goes on, the accuracy gets lower and lower. So we need some way to understand how to understand these kind of trade-offs. All right, so that's an example of a performance characterization. And we do a bunch of performance characterizations. We look at accuracy as a function of various hyperparameters. We look at latency as a function of some parameters. We look at battery as a function of some certain parameters. So these are all characterized offline by doing extensive experiments. And now I'm going to introduce our optimization problem at a high level. So we have a bunch of variables. The variables that we choose to deal with are the camera resolution, the camera bitrate, the frame rate, and which kind of deep learning model to run. And we have an objective. The objective is to maximize the frame rate plus some weighted linear combination of the accuracy. And we have a bunch of constraints. So I'm just going to flash these up on the screen quickly. The constraint is to minimize the end-to-end, or to calculate the end-to-end latency. So the end-to-end latency both includes local processing time plus the network transmission time if I decide to offload. Other constraints include the frame rate constraints, battery constraints, accuracy constraints, frame rate requirements, and the bandwidth constraints. So I just loaded all these up onto the screen, not to scare you with a bunch of equations, but just to give you an idea that there's a lot of moving pieces, right? There's accuracy, latency, battery, all these different constraints on the system. So initially it looks like a very complex problem, has all these variables and so on. But at the end, what we're able to do is show a polynomial time search algorithm, which is also optimal, which is proved in our paper. And the reason we're able to do that is by leveraging certain monotonicity properties of these from our performance characterization. By leveraging these monotonicity properties, we can ensure that the search kind of goes in the right direction and always ends up with the right solution. So I see one question, cool, in the chat. So from Nathan, and it says, do you model noise and channel for the wireless environments? So in this work, we kind of took a more higher level approach. So we just assume that the wireless channel gives us like latency. I guess latency and bandwidth are the main things we consider. So we assume there's like transport layer protocols that are taking care of packet losses and so on. So we don't model the wireless channel at a low level. We just assume we can get latency and bandwidth on average from the system.
Very cool. Can I ask a follow-up? Where do you get the latencies from? Are you like just deploying something and then averaging it, or?
Yeah, so what we do is we send little probe packets in our system. So we initially send probe packets and just count the latency from that. And after the system is operational and like data is flowing between the device and the server, then we keep monitoring how quickly those packets get received and their throughput.
Awesome. Thank you.
Thanks for the question. So here's a little before and after. I mean, there's plots and stuff, but I think people always like videos better. So here's the same before video I showed you where these annotations are not really popping up and they're quite slow and they don't really, they're kind of wrong in the dining table. Right, so that's the same video I showed you earlier. So after we run our system and we do a bunch of optimizations under the hood, I can't really show you what those optimizations are, but hopefully you can take my word for it that we're correctly choosing the camera resolution, we're correctly choosing the right deep learning model and so on. So after we run all these optimizations, what the end result to the user is you're going to see many more annotations popping up. Still not perfect. I mean, you can see the annotations are kind of off, but it's detecting books as my pile of papers, cup, potted plant, and so on. So you see many more annotations popping up and they're popping up much more swiftly. So that's what we want to see. And if the network conditions change, the optimization decision engine would automatically adapt the configuration to keep the good performance. Great. So the main takeaways from this are that the real-time video analysis on using deep learning can be quite slow, 600 milliseconds on current smartphones. There's a complex relationship between the degrees of freedom and the metrics, and it requires offline characterization or profiling. And we need to choose the right device configuration. The specific things we played with were resolution, frame rate, which choice of deep learning model to meet the application requirements. Whoa, all right, great. So that's that's the first piece of work, and I'd be happy to take any questions. Maybe we'll take a quick drink of water and see if anyone has any thoughts.
So could you also comment on the previous video where you said there are more annotations popping up? In this case, your focus was mostly to get to things which are in line, but not necessarily accuracy of these annotations or how to prune them further. And then those are not the current focus in this particular case.
Yeah, so we didn't try to prune ones. Maybe I guess you're kind of getting the point that if it's like too cluttered, the user could get confused. So yeah, we didn't try to prune anything there. We did try to maximize accuracy, but as you can see, it's a little bit off. I think that's also what you're trying to point out. So yeah, I think there are definitely further improvements that could be made, but in the end, I guess, yeah, because the annotations are kind of drifting off a little bit. But in the end, that's the kind of performance we wanted to get. And when we measure that, at least compared to the baselines, we find that the accuracy is much better. But yeah, there definitely could be, some things are wrong, as you can see.
So one curious thing, which maybe there is some reason behind, is that same things are being annotated multiple times. So for example, TV monitor comes up, there's a bounding box, and then there's another bounding box, which is inside that bounding box. What is causing that artifact?
So yeah, that's a great question. So here in this example, even you can see on the screen, it's showing the dining table, and then it also thinks it's the sofa, right? It's overlapping. That depends on the internals of the machine learning models. So with other newer machine learning models, actually, we don't see as much of this because it suppresses things when there's too much overlap. But we do find it's kind of challenging, especially in scenarios where there are like many objects in the screen. We kind of get those effects. But yeah, in later machine learning models, we kind of see better performance than this one. This is like a little earlier prototype.
Thank you.
Thank you. Great, so I'll move on and let me just check how my timing is doing. So the second piece of work I want to talk about today is trying to improve multi-user AR apps through efficient communications. So what are examples of multi-user apps? Example is Pokemon Go. There's a Buddy Adventures feature in Pokemon Go, which lets multiple users here view the same set of virtual Pokemon in the same real world space. Similarly, Minecraft has a feature where you can have multiple users here and they're all viewing the same virtual Legos and interacting with it. Or Just a Line here also has multiple users, and these two users are playing virtual tic-tac-toe by drawing graffiti in the air with their fingers. Cloud Anchor and Vin's AR are other examples of multi-user AR. So before I jump into the details, I need to first give you some background about how multi-user AR works. So we're going to have two clients in this example, client A and client B, Alice and Bob. And Alice is going to initialize the session. So initially she comes in and she scans the scene and she realizes there's a bunch of feature points illustrated by these orange dots. So she scans the scene and then she transmits the information about those orange dots or the features to the cloud. And at the same time, you see this virtual object here, this orange star, it appears on top of the real world table. Next, Bob joins. So Bob is going to come into the same place, and he's also going to scan around the world, and hopefully you could see it there. He also sees the features in the scene, so the corners and edges of the table here. After he scans the scene, he uploads his data to the cloud. Oops. The cloud synchronizes this data, and Bob receives the results and also is able to see the same virtual star on top of the table. So let me just show that part again. Bob sends the data to the cloud, gets synced up, and the same virtual object appears. It was a virtual plane and it flew away. So you see there's two steps here. Alice first joins, initializes the session. Bob then also joins, shares some information with Alice. They synchronize themselves, and then they see the same virtual object. So how long does this take, right? We kind of showed Alice and Bob just in those graphics, but how long is the end-to-end latency of this whole process? So I've shown you this graph before, and this is the end-to-end latency measured between Alice and Bob from when Alice places the virtual object to when Bob sees the virtual object measured over LTE network. And we use existing AR apps on Android smartphones. So I showed you this before, the end-to-end latency was quite high if you look at this CDF. So we want to dig further into this end-to-end latency. Can we break down this latency into its constituent components? So in this plot, we show the latency on the y-axis, and on the x-axis, we show different components of the latency. And what we can basically see is that the majority of the latency is consumed by visual data transmission. So that's the communication here between Alice and Bob. And there's also a bunch of communication, or a bunch of latency resulting from cloud processing. So for this work, we decided to focus on the communications part. And we further measured this communication latency for a bunch of different AR apps. So here we measured the latency from Cloud Anchor, Just Align, Minecraft, and Pokemon Go. And these are just off-the-shelf demo apps or published apps in the App Store. So on the y-axis, you see the latency just from the communication component. And we can see apps like Cloud Anchor and Just Align exhibit multi-second latency. Whereas some other apps like Minecraft and Pokemon Go actually exhibit lower latency, but that's because the placement of virtual objects is not very accurate, I would say. So they don't care as much about the synchronization aspect, and they don't spend a lot of time syncing up the two devices properly. Cloud Anchor and Just Align do take more time, and that's why we think there's a problem here, and we further focus on these two apps. Also, the general measurements that we take, Cloud Anchor and Just Align, are built on top of the AR core platform. So we find that many of the apps built on top of this AR core platform have this problem. So let's look at a network trace. What is happening when Alice sends data to Bob? This is a Wireshark trace. And what you see is that there are several components. So in the first stage, the two devices are syncing up with each other, sort of pairing with each other using Bluetooth. And they're also doing the initial environment scanning. After they scan the environment, then they send this spike of data, which is the initial visual features from understanding what's happening in the real world scene. Then there's a bit of processing time on the cloud, where the devices are doing some computation to synchronize their coordinate systems. And finally, these little blips of data here are user interactions, where the user is like tapping on the screen or drawing like virtual graffitis. So we can see that overall, the time from when we started, right over here, time 0, to when we actually started interacting with the app is quite long. It was almost 30 seconds from this 0 point to the user interactions. So this is from this, we can see that the latency is quite long, and the initial visual features also contributes to the latency in the multiple seconds of time here. We also notice that this initial visual features that are sent impact the accuracy. So I showed you this picture before as an example of accuracy, where the virtual object was placed slightly different for the two virtual characters. So it turns out that these initial visual features sent during this spike of data impact the spatial accuracy. So we also want to understand what is the impact these features have on the spatial inconsistencies that we observed. All right, so that's sort of setting up the problem and all the measurements that we took to figure out what was going on. And the general problem that we have is that multi-user AR apps exhibit these long initialization latencies and high spatial inconsistencies. And our goal is to try to reduce the initialization latency while hopefully improving on the spatial inconsistency, or at least maybe maintaining the spatial inconsistency without making it worse. Because like I said, there's trade-offs between latency and accuracy. So sometimes you get one, but you can't get them both at the same time. So our approach is called SPAR, which stands for Spatially Consistent AR. And I'll just overview the main modules here before I go into a little more detail on a few of the modules. So the first component is we need to adapt the data that's sent between Alice and Bob based on some criteria that we determine. And we're hoping that by adapting the data that's sent between Alice and Bob, we can reduce the latency of the network transmissions. Once that Alice has sent the data to Bob, then Bob needs to do some computation or thinking to reconcile their two coordinate systems and view the virtual object at the same position. So if we have a good method of synchronizing their coordinate systems, hopefully we can have low spatial inconsistency. And the third component we have is an automated tool to quantify spatial inconsistency, because when we were running this, started this project, it ended up being very tedious to sort of manually label the accuracy of the positions of the objects, virtual objects. So instead of spending a lot of grad student hours, we wanted to make an automated tool to do this. So these are the main modules of the system, and I will talk about maybe the first one or the third one in more detail now. So the first question is, what data should Alice send to Bob? And we need to understand what shared data is needed for synchronization. So we could either send camera keyframes. Keyframes are important frames from the user's point of view as the user walks around the scene. So if I send these camera keyframes, they end up being quite large, 150 kilobytes per frame, which sounds small until you realize you need to send a whole lot of frames, maybe hundreds or even thousands of frames. So we don't want to send those because they're kind of large. We'd rather just send the keyframe features, which are features extracted from the keyframes, and those are needed for our synchronization and map alignment steps. And those only consume maybe 20 to 50 kilobytes per frame. And we also have this thing called the keyframe database, which also ends up being needed to correctly match keyframes from between Alice and Bob. That keyframe database ends up being really large. So we have two options of what data Alice should send to Bob. Either Alice can transmit her keyframe database to Bob. So Alice is in blue here and Bob is in orange. And that would give us a 50 megabyte data transmission. The other option is that we could have Alice transmit her keyframes to Bob. So here Alice's keyframe is in blue and Bob's keyframe database is in orange. And that would be a much better solution because it only requires 50 kilobytes per frame. So between these two options, we obviously prefer the cheaper one, send less data. So we choose for Alice to send keyframe features to Bob. So how should Alice filter these keyframe features that she's sending? So we propose a couple of strategies, and this is the main, I guess, key idea of this work. So Alice is moving around on some trajectory in the world, and she captures a bunch of keyframes based on where she was. And some of these keyframes are pointing towards the virtual objects. Some of these keyframes are pointing away from the virtual objects. So our main idea here is that Alice should only send those keyframes that are related to the virtual object. Can we use the context about the virtual object to intelligently filter out which keyframes Alice sends to Bob? So we propose a couple of strategies. One is called SPAR small, and here I've outlined them in yellow. And what SPAR small does is it sends features from keyframes that are close to the virtual object within 1 meter. We also have another strategy called SPAR large, and that is a little more liberal, and it sends keyframes that are a little bit far away from the virtual object, but the virtual object also has to be visible. So for example, these two keyframes I'm showing you here, although they are close to the virtual object, they are not sent because they're oriented away from the virtual object. And we also have two baselines. One is called all, which sends all the keyframe features. And one is called AR core, which is an additional baseline based on off-the-shelf systems. So what we really want to get, hopefully, is our accuracy to be good and our latency to be low. So what we'd expect is maybe this all will probably have high latency because it sends a lot of data, but it should maybe also have high accuracy because it has full information. Whereas with SPAR small and SPAR large, we're a little more conservative with what we send. So the latency should be lower, but the accuracy may also drop a little bit, hopefully not too much, just because we are sending less, there's less information being sent. But actually, surprisingly, as I'll show you in the results, this all baseline doesn't really have good accuracy. And I'll explain why when we show the results. So we also have a tool that quantifies some spatial inconsistency. And like I said, the problem here was because manually annotating the position of the virtual objects ended up being really time consuming. So we developed an automated tool that only requires paper printouts. In the interest of time, I'll probably just skip over this slide. But for details, you can check out the paper. But here's just a picture of our setup. So you have the two devices, you have a printout placed in the scene to enable the tool to work, and you have a grid paper here, which is used for evaluating the performance of the tool. So we did evaluation with different scenarios, different mobility patterns. One is where with Alice and Bob just move side to side, that's scenario one. Another is where Alice and Bob move in a circle. And the third scenario is the most challenging, which is where Alice and Bob start at different locations and they rotate around the virtual object. And we did these experiments both in a home setting and in a laboratory setting. So here's an example just from Alice's point of view. So Alice is starting here and she looks at this virtual object and she sees it on the screen, and then she's going to do a little tour around the lab. So she's walking around our very messy lab. This is before, pre-COVID times and before we got shut down. So she walks around the lab, she comes back to the desk, and what she sees is the virtual object is kind of floating off in space here, and eventually kind of fixes itself. So this is an example of what Alice sees. So let's look at some results. So we want to see how how SPAR system impacts spatial inconsistency. And here we've shown all SPAR large and SPAR small. So the x-axis are different strategies, and the y-axis are different spatial inconsistency, the spatial inconsistency measured. And we do this for each of the three scenarios. So what we find is that the bars for SPAR small and SPAR large are lower than the ones for all, which is what we wanted because we want lower spatial inconsistency. And surprisingly, we also find that the all strategy, despite having full data, actually has really bad accuracy. The objects are off by an average of 20 to 25 centimeters. And we realize this is because the all baseline does badly because it's kind of sending too much data between Alice and Bob. So when they send too much data to each other, they kind of get overloaded. They don't know how to synchronize properly with each other. And that leads to this really poor spatial inconsistency issues. On the other hand, our approaches, SPAR large and SPAR small, because they kind of filter out what data is sent between Alice and Bob, it makes it easier to do the synchronization computations. And in the interest of time, I'll skip the right plot just so we can get to some interesting results. We also look at latency. So this plot is on the y-axis the latency, and the x-axis is the different strategies, including the all and AR core baselines. So again, what we see is for SPAR small and SPAR large, the bars are lower than the baselines, especially in scenario 1 and 2, which are the easier scenarios. So we can basically save a bunch of latency. We do note there are really challenging scenarios. So the most challenging scenario is this scenario 3, where users are rotating around each other and start off from different points. So in those cases, SPAR is kind of doing on par with the baselines. And we think that's an acceptable performance. We didn't gain on latency here, but we managed to gain on the spatial inconsistency from the previous figure. So our conclusion is that SPAR can reduce the latency, especially in easy scenarios. Scenario 3 is challenging because of the user mobility and the different points of view. In the interest of time, I'll just skip this slide. And so the key takeaways basically are that we have these multi-user AR apps that exhibit high initialization latency and spatial inconsistency. And SPAR is trying to intelligently filter out which data is sent between the two users. And SPAR can reduce latency by up to 55% and spatial inconsistency by up to 60% compared to our baseline with off-the-shelf systems. Great. So that's the second piece of work. And then I just wanted to really briefly outline some future directions. So one of the things we observed was that we took these traces of AR apps and we looked at the kind of data that's sent over the network. So we noticed that there's different types of data. There's these big initial spikes, and there's smaller spikes later on from these user interactions. So one question we're thinking about is, instead of making the application aware of the network, how can we make the network aware of the application? So can we have the network, for example, which have different QoS bearers, can we try to map these application data onto these different QoS bearers based on their importance to the application? So I've been reading a lot about 5G recently. There are a lot of nice QoS bearers or different kind of QoS constraints or flow definitions in 5G. So how can we map these kind of AR data onto these QoS bearers? Another piece of work is how network AR architecture should look like for AR. So when we look at different AR platforms, we either see cloud-based platforms or peer-to-peer type platforms. So we don't really understand what are the trade-offs for these different network architectures, because, cloud maybe is more compute, but it has privacy drawbacks. Maybe peer-to-peer is slower because it has less computation power, but it has better privacy. So what are the trade-offs if we look at these different network architectures to support AR? Why should we choose one or the other? And the third thing I'm interested in is more related to the deep learning line of work. So I told you that in the first piece of work, Deep Decision, we had to do a lot of offline profiling to understand how the accuracy, latency, battery changes a function of different hyperparameters. And this is pretty tedious. It's okay for a research project, I think, but it can get pretty annoying if actual users want to deploy it or want to run this on different hardware. So one thing we're thinking of doing is developing post hoc models to try to understand or predict the performance and resource utilization of these deep learning models on different devices. And I know there's been some work on resource utilization for this prediction, but on the performance aspect, I haven't seen as much. So that's a topic that we're really interested in. And if I make these predictions of performance and resource utilization, can I also give us calibrated confidence estimates of how good those predictions are? And then once I have these predictions, can I then use them to make better offloading decisions or configuration choices? So that's all I wanted to say. I wanted to just wrap up with a few take-home messages. So the first thing I want you to remember is that VR is not the same as AR, which is not the same as video streaming. The first piece of work, we talked about how deep learning, machine learning-based AR needs fast, accurate, and energy-efficient deep learning. In the second piece of work, we talked about how SLAM-based AR has high initialization latencies due to the large initial spike of data communicated between the users. And I talked a little about future work that I'm interested in, like making the network AR application aware, and also understanding how to predict the performance of deep learning applications so we can make better decisions. So with that, I'd like to stop, and thank you very much for your time. I really appreciate it, and happy to have any discussions either now or later on.
Thank you so much, Jiasi. Any questions from the audience? We still have a few minutes. Okay. If not, actually there is a question from Aiden. So do you think hybrid cloud / local pipelines are promising? For example, run reliable SLAM in the cloud and then use low latency visual odometry on device to capture motion between the delayed cloud position updates?
That's a really great question. Thanks, Aiden. So there's actually been some work related to that. There's been some papers recently where, kind of like what you said, they run like the heavyweight components of SLAM on the edge or like the cloud. They use the edge though, and then they run these like lightweight components of like the IMU, the visual odometry updates on the device to provide more, to kind of cover the time in between the delayed updates, as you said, from the cloud. So yeah, people are basically working on that. We're also trying to understand, so people have done that in a single user scenario. So one piece of work that I think, or one direction I'm interested in is understanding how that works in the multi-user scenario, because with the multi-user, you have the cloud processing has to be kind of joint between multiple users. So we're trying to understand, does that kind of partitioning that you're talking about, does that also work well in multi-user scenarios? But yeah, people are basically thinking along those lines.
Okay. So the next one is from Joe Young. Do you have thoughts on how LiDAR could integrate with this, for example, on iPhone 12 Pro?
Yeah, I was really excited when I saw that the LiDAR is on the iPhone 12, because I was thinking, what are they going to use it for? I assume it's for face detection, like the security thing, or AR. So I think that's really cool, because it probably means that really cool AR applications can come out. So I basically think the LiDAR will make the computation easier on the device, especially in the SLAM-based AR. It'll make the SLAM more accurate because LiDAR gives you better sensor information, so you can have better estimates of the real world. But I think you'll still see the same communication problems, because once LiDAR has collected the data, we processed it, we still need to share that with other users. So I think we'll see, if anything, even more data that needs to be shared, because the LiDAR data is going to be higher resolution and more accurate. But personally, I'm really excited, and I actually really want to try to experiment with those LiDAR-based systems. Although it's a little bit hard because a lot of these mobile devices are like closed source and it's hard to like play with the internals.
Okay. So next one, Ying Yan, please go ahead.
Okay, thank you. Thank you, Jiasi, for the nice talk. So in this summary, item 2, you mentioned fast, accurate, energy efficient deep learning are needed. So we know, as we know, there are quite some work developed recently. So could you comment what are still missing?
Yeah,
So,
definitely. Yeah, I totally agree with you. So the kind of numbers I was showing you, like these 600 milliseconds was, a few years ago. And I know like, a deep learning for mobile devices is like an insane, very popular topic, and everyone's doing like quantization or having like hardware, TPUs and GPUs and so on to work. So my premise is that on one side, we're going to have people are going to make these models better and more accurate and more efficient. But I also think that the needs for the AR apps are going to grow. So right now the AR apps are just doing really simple they're just detecting like, I don't know, if there's a plane in the scene, like a flat plane in the scene, or if there's like a face that needs overlay on top, right? And those are the typical kinds of machine learning or deep learning uses that we see in AR. But I think in the future, there's going to be more complex deep learning needs from AR. So like lighting estimation is one of them. People want to use lighting estimation to make the holograms integrate well with the real world. And right now I've seen a lot of work on like doing that on a desktop PC with deep learning, but eventually we want to have those things running on a phone, right? So I guess the short answer is basically, I think the deep learning networks that people are going to want to use for AR are going to get more and more complex. So we need to keep working on, at the same time, making these networks more efficient to run.
Yeah, very good point. Thank you.
Thank you.
I just wanted to say, so there's no more question. I just wanted to, I guess that brings us to the end of the talk. Thank you again, Jiasi, for the wonderful talk. And thank you everyone for joining us today. I hope to see you all in our next seminars.
Great, thank you everyone. Bye-bye, take care.